Hey everyone, and welcome to This Explainer. Today, we are going to uncover the invisible rules that completely govern every single physical movement we make. Seriously, we move through our days taking the incredible unseen physics happening around us completely for granted. Every time you open a door, take a step, or even just drop a pencil, there is a whole lot of science going on. So today, we're going to make the invisible visible.
Okay, let's kick things off with a super simple question. When you roll the ball across the floor, or say when you stop pedaling your bike, why does it always eventually come to a dead halt? I mean, it doesn't matter how hard you push it, right? It never just keeps going forever. There is actually a hidden director orchestrating exactly how and when things move and exactly how they stop. To get to the bottom of this, here is our agenda. We'll be looking at 1. The invisible push and pull, 2. Contact and non-contact forces, 3. Friction, the motion stopper, 4. 3 kinds of friction, and 5. Controlling the friction frenemy.
All right, let's jump right into section 1, the invisible push and pull.
Think about this for a second. Whether you're stretching a rubber band, blowing up a balloon, picking up your phone, or kicking a ball, you are applying a force. And at its very core, in the language of physics, a force is fundamentally just a push or a pull. That's it. You either push something away from you or you pull it towards you. That simple action is literally the bedrock of all physical activity in the universe. But here's the thing. Force isn't just about getting things moving from a standstill. It's incredibly versatile. Applying a force can completely stop an object that is already moving. It can alter an object's speed, like making a shopping cart speed up or a bicycle slow down. It can totally change the direction of a moving object. And amazingly, it can even change the shape or size of an object entirely. Just think of compressing a metal spring or stretching that rubber band. Force dictates absolutely every change in state.
You see this in action everywhere in your daily life. Take a kid pushing down on bicycle pedals. That applied force takes an object that was at rest, and continuous pushing makes it go faster and faster. But then, contrast that with a goalkeeper catching a massive football. That goalie is applying a force in the exact opposite direction of the ball's motion to bring it to a very abrupt stop. It's the exact same fundamental concept, a push or a pull, yielding completely different results.
So now we know what force does, let's look at how it actually gets applied to the world around us in section 2, contact and non-contact forces.
In physics, we basically group forces into 2 main buckets, all based on one simple rule: touch. First, we have contact forces, which absolutely require physical touch. When you use your muscles to lift a heavy box, or when your shoes grip the floor, those objects must interact directly. But then we have these almost magic-like non-contact forces. These act invisibly on objects from a distance, without any physical connection whatsoever.
Think about a non-contact force in action. A bar magnet pulls metallic clips and iron nails right over to it without ever actually touching them at first. As you move the magnet closer, the clips just jump up to attach to it. It's exerting an invisible field of attraction, and this behaves exactly like the Earth's gravitational pull. Gravity is the ultimate non-contact force, drawing a falling apple to the ground or pulling a basketball straight through a hoop without a single string attached.
Which brings us to one of the most important contact forces we experience. Section 3, friction, the motion stopper.
Remember that question we asked at the very beginning, why a rolling ball eventually stops? Well, here is your culprit. Friction is the force that opposes motion when 2 surfaces rub against each other. And the reason why is mind-blowing when you zoom in. Under a microscope, even a seemingly perfectly smooth wooden table isn't smooth at all. It is literally covered in tiny bumps, little microscopic hills and valleys. When a wooden block slides over that table, those microscopic hills and valleys snag, interlock, and entangle with one another. This mechanical interlocking strongly resists the motion, acting in the exact opposite direction of the motion, gradually slowing the object down until it completely stops.
But it turns out not all friction is created equal. Understanding its different forms is totally key to how we manipulate our physical world. Let's check out section 4, 3 kinds of friction.
This hierarchy is pretty fascinating, and it's all based on how things are moving. First up, we've got static friction. You know when you try to shove a massive heavy table and it just flat out refuses to budge? That's static friction, keeping an object at rest, and it is the strongest of the 3. Then, once you finally muscle that table into moving, you'll probably notice it gets slightly easier to push. That is sliding friction. It resists the movement of an object that's already in motion, but it's weaker than static friction. Finally, we have rolling friction.
When an object rolls over a surface on wheels, only a tiny part of the object actually touches the ground at any given time. Because there's less surface contact, there is far less interlocking of those microscopic hills and valleys. So rolling friction is the weakest opposing force of all.
Because of this sliding scale of resistance, we arrive at our final topic. Section 5, controlling the friction frenemy.
Scientists actually call friction a necessary evil. Kind of a dramatic name, right? But it makes perfect sense. It's evil because it generates heat, wastes precious energy, and literally destroys our machines over time through wear and tear. It's the whole reason the soles of your favorite shoes eventually wear out, and why a car requires so much extra fuel just to push past the resistance of the road. But why is it necessary? Well, because without it, you literally couldn't walk across the room. You'd just slip and fall instantly. You couldn't write on a piece of paper, hold a glass of water, or hit the brakes on a bicycle to stop. We are entirely 100% dependent on it.
So, when friction is acting like our worst enemy, we invent brilliant ways to reduce it. We use oil and grease to smooth out moving engine parts. We use ball bearings to convert that tough sliding friction into weak rolling friction. And we give airplanes, ships, and fast cars aerodynamic, streamlined shapes. By making the front pointed, honestly, much like the body of a bird or a fish, we drastically reduce the friction from air and water resistance. This allows these massive, heavy vehicles to just effortlessly cut through their environments.
But then, on the flip side, when we desperately need friction, we crank it up on purpose. Picture a kabaddi player intentionally rubbing rough, dry soil all over their hands. They need to maximize the roughness of their skin's surface to create enough friction to firmly grip their opponents. We do the exact same thing with our vehicles. Car tires are carved with deep, intricate grooves. Those rough patterns are designed specifically to increase friction between the rubber and the road. It grips the asphalt tightly, preventing the car from fatally skidding, especially when it's raining.
So, we've seen how force kicks off every single action, and how friction dictates exactly how those actions play out. As we wrap up this explainer, I want to leave you with a really wild thought to chew on. If this invisible, everyday force of friction suddenly vanished entirely, just completely wiped from the laws of physics, how completely chaotic would your life become? I mean, you wouldn't be able to stand up, drive a car, or even hold your phone to watch this. The physics of our everyday life rely on this incredibly delicate balance. Thank you so much for joining me on this explainer, and keep looking out for those invisible rules shaping your world.